Hello everybody, my name is Maria Tomé. I am Materials Engineer student of Federal University of Santa Catarina, and this video is a work for a discipline called Topics in Fabrication III, ministered by Professor Fernando Cabral. I'm going to talk a little about tribological behavior of filled PDC coatings applied onto surface of sintered steel. And this presentation is totally based in master dissertation of Priscila Gonçalves. So, the first question for us: what are polymers-derived ceramics? What are PDCs? PDCs are silicon-based ceramics materials in which the transformation of polymers precursor into ceramic occur via thermal treatment. So, to make this transformation, polymer precursor is subjected to polymerization. Monomers form polymers macromolecules. Then this material is shaping and cross-linking happens commonly below 200 degrees Celsius. Above 400 degrees Celsius, reactions and radical rearrangements leads to the break of the chemical bonding and the detachment of non-functional groups from the main polymer chain, macroscopically observed as gas released during the pyrolysis. At 800 to 1000 happens the organic to inorganic transition, followed by a shrinkage over 50% in volume, mass loss, and the density increase. Now we can see the polymer after the pyrolysis became amorphous ceramics. All these steps resulting in a lot of defects as pores and cracks detrimental for the mechanical properties. To overcome this drawback, we can load the polymer with fillers. Fillers in various shapes, sizes, are used to reduce shrinkage and eliminate cracks and large pores. In addition, we also can improve the mechanical, electrical, tribological, and magnetic properties of PDCs or other composites. Here we have an example. Here is without filler, a PDC without filler. We can see a lot of cracks. And here is the same PDC with 50% in volume of alumina, and we can't see the cracks anymore. In this work was employed passive fillers. They maintain the original mass. It means that they don't react with polymers, gas products, or pyrolysis atmospheres during the thermal treatment. And in his work was employed as inert fillers silicon nitride and boron nitride. This is the structure, trigonal alpha silicon nitride and hexagonal form of the boron nitride. The proportion was 65% and 9% of the coating. And the silicon nitride was applied to strengthen the matrix and reduced wear by formation of a network aggregated by the PDC. And the boron nitride was employed to generate lubricating effects on the interface, reducing friction wear and friction heating. This is a microstructure obtained by SEM of the transversal cut of the sample, and we can see the metallic substrate here and the coating, the ceramic coating here, the PDC. This is how the tribological behavior was evaluated. This is a sliding test in which you apply a force of 4 newtons in a rotate spheres that press the sample surface. In this work, the sliding distance was from 30 to 48 meters. Here we have two photos, the uncoated sample and the coated sample, and the graphic of friction coefficient versus sliding distance. The composites didn't present a satisfactory tribological response when evaluated under the tested conditions. The friction coefficient of the composite was between 0.4 and 0.5. were above the lubricious regime 0.2. The coating was prematurely broken, which were in sequence deformed, comminuted, and oxidized by the substrate and counterbody during the sliding test. The major contribution to the friction coefficient behavior was from the substrate, the metallic substrate, but controlled by the formation of the 30 body. What was found is that the test conditions may have been too much aggressive to this coating. So I finished, and thank you very much for your attention, and please let me your like here, and bye bye.